So with that out of the way, let's kick the session off. The session is Thinking Outside the Sandbox, Violating Trust Boundaries in Uncommon Ways with Brian Gorence and Jaisal Spellman. Thank you.
Hello, everyone. Welcome. This is Thinking Outside of the Sandbox. I'm glad you could roll out of bed this morning after probably drinking all night to attend our talk. Jaisal and I are honored to be speaking here today. There's been a lot of innovative exploitation talks this year at Black Hat. We're glad to be part of that list of chosen speakers, and we hope you greatly enjoy the talk and learn a lot of things about sandbox bypasses that you may not know today. If you attended Forshaw's talk earlier yesterday, you'll see a little bit of technique overlap, which is kind of interesting to see that there are researchers all around the world who are finding similar vulnerabilities in the sandbox, and which is allowing them to escape. First, we'll kind of go over the agenda. First, for the people in the audience who've done a little bit of sandbox escape work, you can probably ignore the first two sections. We're going to cover what exactly a sandbox is and how it's implemented, and try to bring everybody up to a point where they can understand the attacks. Then we're going to talk about how you actually attack the sandbox itself and the different archetypes that exist to go after getting privilege escalation. And then we're going to discuss 4 case studies that showed up at this year's Pwn to Own. 2 of them are Google Chrome sandbox bypasses, and 2 of them are Microsoft Internet Explorer sandbox bypasses. And one of them is actually an active 0-day. We're releasing it today for everybody to see. You can, because Google's patched both of their sandbox bypasses, you can imagine which vendor the 0-day applies to. But we're going to be discussing some of those more obscure techniques throughout the talk. A little bit of introduction. My name is Brian Gorence. I'm the manager of vulnerability research inside of HP Security Research Organization. My primary responsibility is running the 0-day initiative, which is the world's largest vendor-agnostic bug bounty program. Through this program, we've been able to inject over $10 million into white hat research and the vulnerability marketplace to get bugs fixed. We've fixed, over the lifetime of the program, over 1,600 0-days, many in which fall into critical software like Internet Explorer, SCADA systems, and things like that. I'm also responsible for running the Pwn to Own competition. Every year this year, I think at least disclosed 30 0-days to vendors, and I think spent out more than $700,000 to the best exploiters in the world. In my free time, I like to look for bugs, and then when I'm not organizing or running ZDI, I'd like to do case analysis on all the submissions from everybody in the world who submits to the program. Malicious input on Twitter, and I also run the ZDI handle.
How's it going? I'm Jaisal Spellman, and I'm also part of the HP Security Research team. I'm actually Brian is my boss. I'm also part of the 0-day initiative, and as a result, I spent a fair amount of time analyzing the bugs that are submitted to us, as well as analyzing and exploiting any bugs that we find internally. As a result, I spent a lot of time staring at IDA and also instrumenting binaries with pin Dynamo Rio, or even just injecting Python to then have arbitrary assembly inserted into the process. I'm Wandering Glitch on Twitter, and I'm also one of the guys behind the ZDI account.
All right, so what we're looking at today is actually attacking the modern web browser. And if you talk to the people who actually do exploitation against the browsers, they'll tell you that it is getting harder to do this and to actually get code all the way through the browser, through the sandbox, so that you have elevated privileges to do something actually interesting. But if you actually look at the type of attacks that they're using, first they have to find a vulnerability in the actual renderer process, which allows them to get code execution. They've got to bypass all the mitigations that exist, including ASLR, leaking an address to find where their code is running in memory, develop the ROP chain on the fly so that they can bypass DEP. And once they've actually got that code running, it's just running at low integrity. And then at low integrity, you don't really have access to a lot of resources and stuff that will allow you to persist a piece of malware. Along with this, the developers of the browsers are implementing a lot of new mitigations. If you look at partition alloc and oil pan and Chrome and Microsoft's recently released yet not announced use after free mitigations called isolated heap and memory protection, they're doing a lot of work to stop exploitation of some of the most common vulnerability types in the renderer process. But once you have that code running at low integrity, you need to actually break out of the sandbox to do anything interesting. And so that's where this talk actually starts. We're going to make the assumption that you have code execution in the browser and you need to attack the sandbox to elevate privileges so you can do more interesting things. But first we need to understand what exactly a sandbox is. And if we look at this from an academic perspective, all the application developers are trying to do is create a clear separation inside of their application where data crosses a boundary of trust. This boundary there on one side is untrusted processing, on the other side is trusted processing. And at this boundary, they can actually validate the input that's coming in and enforce a set of security policies to verify that the code that's coming in should be allowed to run in elevated privileges. They are actually considering the fact that their untrusted code actually contains 0 days and code execution vulnerabilities in them. If you look at a lot of the 0 days that are released or actively in the wild, the first mitigation that Microsoft releases is go enable enhanced protected mode and go enable emit to actually stop it. They're relying heavily on these the Sandbox implementations to actually stop the 0 day attack from being useful. But if we want to understand exactly how it's implemented, we need to go back to 2007 when Microsoft's David LeBlanc released a series of blog posts called Practical Windows Sandboxing, where he released a set of best practices for application developers to use to sandbox their application. Obviously, the vendors take these best practices and implement them to varying degrees, but the first recommendation that he actually provided was that the process that is running should be running using a restricted access token. What exactly is an access token? It identifies the privileges of the user account associated with the process. And a restricted access token is exactly what it sounds like. It's an access token that has restricted SIDs, disabled security identifiers, and deleted privileges. And what you see on the screen is the access tokens for both Internet Explorer and Chrome. And you can see the level of difference between the two sandbox process, where Chrome really has no privileges assigned to it, and Microsoft's Internet Explorer does have some. Google Chrome has a lot more denied SIDs than Microsoft Internet Explorer. Why that is, I don't know, but as an application developer, if you want to run with a restricted access token, you should be using create restricted token or adjust token privileges API calls to get those tokens. The next recommendation that LeBlanc suggested was that application developers use what's called a job object. A job object is a mechanism in the operating system to manage a group of processes as a single unit and apply restrictions to that single unit that get applied to the processes that are associated with it. There are a lot of limitations that you can actually implement using a job object. First is limiting the number of active processes associated with the job object. In the case of what you see on the screen, that's Google Chrome's job object, and they restrict access to active processes to 1. Along with, there's other limitations that can be applied to the job object, including creating and switching desktops, exiting windows, reading and writing from the clipboard, and changing system privileges. And so what you see, in fact, Google Chrome actually uses the job object. They apply almost every restriction that's available to the job object, where this is the same for Adobe Reader. Internet Explorer does not use a job object at all the last time I checked. So, I don't understand why, but that's what they do. They, I'm sure, have other restrictions. The final recommendation for a sandbox application that LeBlanc provided was to run on an isolated Windows station and desktop. A Windows station as desktop is a mechanism inside of the operating system for managing user interface objects. For a Windows station, it provides a clipboard, it provides an atom table, it provides the desktop itself, and the desktop actually provides all of the user interface objects like windows, menus, and things like that. The interesting thing is all the processes that are associated with a single desktop can communicate with each other using window procedures and window messages and hook procedures. And actually, in the past, there was an attack called the shatter attack that actually allowed you to elevate privileges by using window messages and hook procedures to elevate privileges in other processes that are running on the same desktop. The idea of isolating an application on a unique desktop is to reduce the ability for a compromised process to move laterally throughout the other processes that exist on the same desktop. And so you'll see Google Chrome's renderer process runs on its own desktop. This is actually important to understand for an attack that we're going to show later that takes advantage of a clipboard attack. So one of the most, popular ways to actually implement the sandbox, combining all of those things along with mandatory integrity controls, which were introduced in Microsoft's Vista. There are 5 levels in the operating system for integrity, and they really represent the level of trust in a process. Lower integrity processes don't have access to all the resources that a higher integrity process would have. So you can see in Internet Explorer, if you run Process Explorer, and you'll see that later in the presentation, the renderer process itself is running at low integrity, where the broker code is running at medium integrity. In Google Chrome, they decided to use the untrusted integrity level for their renderer and medium integrity for their broker, and we'll show you both of those later. Another interesting thing that they introduced in Windows Vista is the user interface privilege isolation, which prevents lower integrity processes from sending window messages and hook procedures to higher integrity processes, effectively trying to stop shadow attacks and privilege escalations that way. Next is sandbox communication. If you try to isolate your application, it still has to provide a certain level of feature set to be competitive on the market. And so the application developers have to communicate, this low integrity process has to communicate back to the higher integrity part of the application to actually provide these elevated privileges, this elevated functionality. And this communication usually takes place in 2 different types. In Google Chrome and Adobe Reader, they're using a shared IPC interface to actually do this broker communication, providing the APIs for the broker, and you'll see a couple of those later in the presentation. And Internet Explorer, majority of its elevated privilege processing actually happens through COM objects. At this point, these APIs actually enforce all of the validation and the security policies, so they make sure that files aren't being written outside of the sandboxed areas and making sure that the information is valid as it crosses that trust boundary. There are other sandboxing technologies, things like App Container, recently in Windows 8. Some of these things aren't on by default, so we didn't include them in the presentation. I guess if you're using Metro mode, you get access to App Container by default, but I don't think anybody actually in this audience uses IE in Metro mode, so we didn't include it in the presentation. Next is now that you kind of understand how a sandbox process, or how you actually sandbox a process, we're going to look at how you would attack that implementation and what are the most common techniques for doing this. First is finding a vulnerability in the kernel. Obviously, this is game over. If you have a vulnerability in the kernel, you can get system-level code execution or privilege escalation. And this is obviously, would be much more valuable than actually medium-level integrity code execution. The issue is the kernel vulnerabilities are difficult to discover. They do happen, but that code is typically gone through a lot of security reviews, and it's highly tested prior to its release. So it is more difficult to find, but at the last 2 years of Pwn to Own, contestants have brought in system-level privilege escalation bugs as part of their attacks. And what you see on the screen is actually a picture I took at Pwn to Own when we were disclosing to Microsoft this exploit. It's Sebastian's and Andreas exploit. It's what you see on the screen is actually a system-level calculator running, which is obviously not supposed to happen. But in Pwn to Own 2013, yeah, it's pretty common. At Pwn to Own, at least, it's common. The system level in 2013, there was a system level compromise through Google Chrome. John Butler and Nils from MWR Lab abused a vulnerability NT-user message call. Is that what it is? Yeah. And it was due to the way that function call actually misused a Boolean argument. That was a slick bug. And in 2014, this year, there was a vulnerability system-level compromise through Internet Explorer, where Sebastian and Andreas abused a couple use after freeze to get code execution in the renderer process. And once they were running there, they abused a double free vulnerability in the afd.sys driver to gain system-level code execution. And I believe, correct me if I'm wrong, but that actually won the pony for the best privilege escalation for the year. That was a killer bug. There's a badass write-up on the internet, so you should go check it out. Next, beyond looking just at the kernel, which is actually a hard attack surface, there's the going after the actual IPC and the communication mechanisms that are implemented by the browsers. There are the most common types for abuse of broker APIs. First is memory corruption, where the broker actually mishandles the parameters that are coming in from the low integrity process, and there's also logic errors where you're able to bypass the security policies and elevate privileges that way. Two case studies that we're going to look at is Adobe Reader's, the first Adobe Reader Sandbox escape that was found in the wild. It actually abused a heap overflow in how the sandbox or the broker actually handled get clipboard format name W. And with that heap overflow, they were able to break out of the sandbox and elevate privileges. Next is Microsoft's Internet Explorer CVE 2013-4015. This we consider a logic bug inside of Microsoft's get sanitized parameters from non-quoted command line method call. In this, it's a long API call. In this case, this method didn't properly handle the tab whitespace character, and as a result, an attacker who had code execution in the renderer process could launch an attacker-controlled specified executable name through the broker and effectively elevate privileges to medium. Next is actually shared resources. This is actually becoming pretty common. When you look at a shared resource or access to handles or sections or registry keys, this sharing or leaking of handles typically occurs either directly from the broker to the lower integrity process or from a third-party DLL that provides back to the low integrity process a privileged handle. If you have write access to this handle, it might provide an opportunity to escape depending on how the code actually uses the handle. You'll see later on one of the Google Chrome Sandbox bypasses abuses a privilege handle in a unique way that is, in fact, one of my favorites. In this case, browser developers are taking an active approach against this abuse of shared handles by restricting the DLLs and executables that are allowed to be run by low integrity processes. This is typically, in IE at least, called elevation policy, which we'll show later as well. There are additional vectors to bypassing the sandbox that have come up in the past. Researchers have abused base named object namespace squatting, null DACLs, and we actually released a socket-based attack against last week against Microsoft's Internet Explorer that worked against the default installation of Internet Explorer 11 on Windows 8.1 using a socket-based attack. The blog is out there. It's a really interesting technique to bypass protected mode. Application developers, though, are, in the end, have to balance the security of an application and the function and the feature set that they have to provide, and so it may provide that you, as an attacker, access to escape the sandbox. And Jazel's going to come up and start describing some of the attacks that we saw at Pwn2Own.
All right, so the way we'll do this is we'll show a video of the exploit actually taking place, and then we'll go into the details as to what the bug is and how they were able to exploit it. The first one was brought to us by Vupin. They actually found this in 2011, though they brought it to Pwn2Own in 2014. It started off with a use after free in Flash in the external interface object. It was CVE 2014-0506. And the issue is a logic bug in the handling of the save as dialog bug, or dialog window. And I apologize, the spray is a bit long, so bear with me a sec. And despite the fact that this does require user interaction, there's no good response despite what they're doing. I should have recorded mouse movements. I'm actually going to hit cancel for this window, and I'm not going to allow the file to save. but we'll see in a second that a file was actually written. So there's hello.hta, and at the bottom of it, although it's a bunch of binary, there is some controlled string at the bottom that in this case will execute calc, but could do anything. So first you need to understand why this sort of functionality would exist. A renderer process runs at low integrity and as a result can't save files to places like in the desktop or the downloads folder or documents, wherever, places a user would actually want to save things. As a result, the broker offers two COM methods to allow for this. The first is in the C-protected mode API object, show save file dialog. And as the name implies, it shows a save file dialog, the one you see on the right side of the screen. The renderer can specify a default path to use, at which point the user can overwrite and change it or do whatever. If the user then hits save, a message is sent back to the renderer. The renderer then downloads the file to some location that is writable by a low writes process, and then it calls the save file as function. Despite the name, that function actually just functions as a move and will move the file that's specified as an argument to the file that was specified to show save file dialog. And the issue here is that in show save file dialog, Microsoft they had a logic bug. One issue with this is downloaded files have the mark of the web applied to it. So if someone were to save a file to the startup folder, then when the user logged back in and Explorer tried to execute it, it would prompt the user and make sure that they want to execute it. So there was something else that they had to do. To use that, or to get around that, Vupin used the C recovery store, which is responsible for storing data about a currently open tab. Anyone that's ever written an exploit for IE that wasn't successful the first time knows that IE is nice enough to run it again, and that's thanks to the data stored by the C recovery store. The file is stored in a predictable location. However, it's an OLE container, and as you saw in the notepad window during the video, it has lots of binary. Thankfully, the renderer controls the string or the title that's written, as well as the URL that gets written. And the HTML application parser is incredibly lenient. This is the parser that handles .hta files. It will look for any script tag within the given file, and as long as it finds a script tag, it'll execute whatever's in it blindly. So putting it all together, Vupin triggered the use after free in Flash, controlled it, and then made a broker call to show save file dialog with the destination in the startup folder, and you can see on the right side of the top that they're setting the string to hello.hta. They then made a call to set current title, which I should have pointed out on the previous slide. Here you can see that they're controlling the string and putting malicious script inside it. And then they're calling save file as, and they're setting the source as the recovery store. So they're controlling the source and the destination and part of the string inside so that they can execute calc. The bug itself is due to the handling of the state in show save file dialog. It assumed success and would only reset things if a failure had occurred. As a result, despite the fact that I hit cancel in the video, the write was still able to be performed. All the renderer has to do is immediately issue this call to save file as, and then you'll be able to have an arbitrary file rate. To remediate this, Microsoft ended up just doing the obvious thing, which is only move into a success state when they've actually guaranteed and confirmed that the user does indeed want to save the file and that there were no errors raised by the IE get save file name function. In addition, to make things a little bit more difficult, they removed access to the C recovery store. Previously, this was accessible through the broker create known object function, which is a function that's available to the renderer to instantiate a few COM controls. It takes a list of allowed classes, and C recovery store is no longer there. However, you still can indirectly access it through window messages, in that you need to be able to if it's to properly recover a tab. Oh, and Microsoft patched that in June of 2014. It was part of MS 14.035. This next vulnerability is a sandbox escape in Google Chrome, and I think it's my favorite because it's just so interesting. It starts off with CVE 2014-1713, which was a use after free in the Blink bindings. However, despite it being Blink, it also affected WebKit. Vupin then exploited a Chrome bypass in the broker, and then they got exploitation at medium integrity by taking advantage of a buffer overflow in direct show. So here I'll show the video. This one's fairly quick. And so I'm just right-clicking on the desktop, and you can see calculators are just spawning. Definitely my favorite bug. And here in Process Explorer, you can see that all those calculators are running at medium integrity. So to understand why this happens, you first need to understand that all the renderer processes for Chrome run as untrusted, but they also run in their own window station. And as Brian had mentioned earlier, this means that they have their own clipboard and their own atom table. This means that if someone wants to copy data from a renderer process, the renderer has to send it to the broker and have the broker copy it to the clipboard for them. To that end, the broker offers two cross calls, clipboard host message and write objects async, and clipboard host message write objects sync. On Windows, these end up calling the set clipboard data API, which takes two parameters. The first is the clipboard type, and the second is the actual data, which gets handled differently based on the clipboard type. Data is serialized to the clipboard by Chrome, depending on the type that the renderer requested. So if the renderer requested text, then that'll bubble up and end up calling the write text function, and the broker will specify the format type when calling set clipboard data. However, if the renderer requires data, just arbitrary data being put to the clipboard, then the renderer has control over the clipboard, and that's in essence the entire bug. Microsoft explicitly states that clipboard data is not to be trusted and that should be parsed very carefully, and a huge reason for this is clipboard type hex C016, which is an undocumented clipboard type that gets registered by Microsoft. In the Atom table, it's known as more OLE private data, and this can be used to instantiate arbitrary COM controls, which is exactly what you saw when we were just right-clicking on the desktop. COM controls that are instantiated in this manner are not checked against the ActiveX kill bit, and that's how Ruben was able to put all three together and get a direct show vulnerability and get calculators to respond. So all in all, what they did is they took advantage of the use after free in Blink. They then sent a message to the broker and specified that they wanted CBF data, which then grabbed the clipboard format from the data that they were also supplying. And so they supplied both the clipboard format and the buffer itself. When you right-click on the desktop, it then, or just access the clipboard in general, it then instantiates the COM controls, triggers a buffer overflow, and then whatever you want to execute, executes. One interesting aspect about this is depending on how a VM or VNC or our desktop was implemented and how copying is shared between, you could potentially bring this back to you, which is particularly frightening for anyone that does any malware research and does all their work in a VM. Exactly. To fix this, Chrome basically added a list of allowed formats, and when the broker spins up, it starts registering formats that it knows it needs to be able to pass and that it knows it knows are safe to pass back and forth. Then in the write pickle data function, which is called as part of any write to the clipboard, it then does a quick check in is registered format type, and if it's not a format type that it is aware of and likes, it'll just flat out reject and not write it to the clipboard. And now I'm going to pass it over back to Brian so he can go over the next vulnerability.
All right, so this vulnerability itself is actually the 0-day that we're releasing today. And before we go into the details about the 0-day, you gotta understand why we're releasing it as a 0-day. The 0-day initiative has a quite famous disclosure policy that basically provides the vendors 120 days to fix the bug. Microsoft had 120 days to fix this bug and it wasn't fixed. We actually provided them an extension for fixing the bug until yesterday. And so now we're going to release the details for everybody to see because it is still not fixed. This specific sandbox bypass abuses presentation host. And if you watch the exploit on the screen, this was actually brought to us by a combination of Keen Team and Team 509. They came in and exploited Adobe Flash. The initial bug that they used was CVE 2014-510. And the flaw is in the handling of display objects. This error actually resulted in an out-of-bound indexing, which allowed them to gain code execution in the context of the process, where they could go about attacking the sandbox itself. And it's a relatively quick exploit to run. The things to be looking for in the video is first, they navigate to the page, the application, there's a crash that occurs. You see a tab pop up, another tab pop up in the browser, and then another crash and a calculator pops up at medium integrity. They just weren't cleaning up the exploit, so that's why all the crashing occurs, but they are successfully bypassing the sandbox. So we'll run that real quick. So you can see the two tabs and a calculator running, and then you'll see that it is actually at medium integrity. So they've effectively bypassed the sandbox using presentation host, which we'll talk about now. So why is this possible? Microsoft Internet Explorer has a thing called elevation policy. Elevation policy is that white list of applications that can be run from the low integrity process. When the renderer calls create process, it eventually gets redirected into the broker using Microsoft's application shim infrastructure. During the broker calls, there is a set of checks that it does against an elevation policy, which is that whitelist. This policy is actually defined inside of the registry at the location listed on the slide, and it will identify the EXEs that are allowed to be run, or the DLLs, along with the policy value. The policy value itself defines how the broker is going to run the process. If the policy value is 3, the broker silently executes the process at medium integrity. If it's 2, it prompts the user with an elevation prompt before running the executable. The less interesting ones are 1 and 0, where it's running at low integrity, and running at, or 0, which it will just block the process altogether. And so in this case, if you look at the registry for presentation hosts, and it's an excellent target for attack because it is running with a policy value of 3, which means it's running at medium integrity without any intervention from the user. Presentation host provides one argument to it. And so if you can find a vulnerability in the way that presentation host works, you could get medium level code execution through that vector. In this case, the researchers were abusing the way that presentation host uses protocol handlers. If you look at protocol handlers in Internet Explorer, the privilege level of the page is based off of the URI. So if you are using a file protocol handler, the page will get loaded at medium integrity. But if you're in a low-level process, you can't just redirect to a local file. It will actually block that. So you can't do like local.href equals file : / whatever. It won't allow you to do that. In this case, presentation host actually will implicitly call the file protocol handler if you're using localhost $C$ as the location, and then you can basically put any location on the disk that you want to load in to presentation host. And in this case, this is how they ended up abusing presentation host, and we'll show you exactly how here. What the exploit actually does is it first gains code execution inside of Flash. The payload drops a malicious SWIFT to the local low area on the disk. This is a place on the disk where the low integrity process can actually drop files to. And then it calls create process on presentation host with the command shown on the screen, which will load the SWIFT into a medium integrity tab and then exploit the same exact Flash bug again with a different payload. And there you go, you get a sandbox bypass using presentation host. For all of you system administrators in the audience, we do provide remediations for this actual vulnerability. Just set the policy value to 0 in the registry. This will stop presentation host from being run and used as a possible vector. There are a lot of researchers looking at elevation policy stuff, so you can only assume that somebody else has found this as well. Because that seems to be the easiest way to break out of the sandbox. Next is actually my favorite sandbox bypass from Pwn to Own. It's an abuse of symbolic links inside of Google Chrome, which will allow in this case, an anonymous researcher into Pwn to Own to bypass the sandbox. He used CVE 2014-1705, which actually is the same vulnerability used by GeoHot in the Ponium contest, which I believe also won the Ponium award. This vulnerability is an out-of-bound indexing issue with typed array objects, and allows you to read and write to any address in the process, allowing you code execution. It was actually a very popular bug. There was a lot of collisions with this bug out there. So let's watch the video. The other interesting thing is this proof of concept is actually entertaining to watch. It's just not like a calc popping. So he'll kind of give you a step-by-step. Woohoo! So that's the Google Chrome. In this case, we're not going to talk about exactly how he popped calc right away, but we are going to talk about the Sandbox bypass, which allowed him to write out to the startup folder. So to understand what's actually going on in this attack, you need to understand what exactly Google Chrome is doing. Google Chrome actually uses a SQLite database to store information about open tabs. There is actually an IPC call to facilitate this. It's database host message open file. And so the attacker or a person running at a low integrity can provide a controlled file name to that call. And eventually it gets down to this create full file path for VFS file. At this point, it merges a base directory along with the attacker supplied file name, and Google actually does at this point do a check for a malicious intent of that parameter. They are doing a directory, or they did a directory traversal check at that time. They were trying to make sure that the write was not happening outside the sandbox, but the attacker took a different approach. Eventually, the file name goes all the way down to a Windows create file API. But what the attacker was actually abusing is the fact that files that are stored on NTFS contain streams, alternate data streams. You know, they were like popular like 10 years ago. He's bringing it back new again with this one. If you can actually access the streams for an NTFS file using colon-separated values. So he actually appended to the file name colon $I30, which specifies the default stream name, and then appended $index allocation, which allowed him access to the default directory stream for the file itself. When you create a file with this set of stream attributes at the end, will actually set the file flag backup semantic flag implicitly, which is not allowed by the process to begin with, or through the broker. Once this file has been created, it is a handle to a directory stream. This is passed back from the Chrome broker to the renderer process, where the attacker just has to use device IO control with an fsctl set reparse point as the IO control code, and he can produce a junction point to an arbitrary location on disk. In this case, he used the root of the C drive, C:// as the junction point, and at this point he can create and modify files off of this privileged handle wherever he wants. And so he targeted, in this case, the startup directory, and through that he was able to achieve medium level code execution. He was using other techniques to actually get it to pop right away, but this is how he broke out of the sandbox. And what is actually the root cause of this vulnerability? It's some weirdness inside of Windows where a low integrity process cannot create symbolic links, but they can create junction points. And these junction points can be used to get access and acts like a symbolic link for a directory. In this case, the junction point requires the directory handle, but in most cases, you don't have access to the actual create file Windows API to set the file flag backup semantics flag, but you can implicitly set this through $I30 $index allocation and get access to that directory stream, and then which allows you to create a junction point. Google Chrome fixed this by introducing a couple checks. First, they do a check against their platform file backup semantics flag to see if a directory or a reparse point was actually requested. And if not, they make sure that they're not passing back a directory handle or a reparse point to the low integrity process so that they can't create a junction point and write to wherever they want on disk. So in conclusion, application developers are working hard to implement and create sandboxes. They're doing a lot of implementing the best practices, or most of them are. They're trying to restrict the number of APIs. You see recently Google Chrome, some of the members of the Google team tweeted out a way to reduce the type of kernel APIs that are available to the low integrity process. So they are working hard to actually reduce the attack surface. They spend a lot of time obviously analyzing their code, hiring consultants to look at their code to make it as secure as possible. And their primary purpose is to have that clear separation of untrusted processing and trusted processing and enforcement of security policy. This, of course, though, drives the next evolution in exploits. There are many techniques that are very popular to actually break out of the sandbox, things like kernel vulnerabilities or vulnerabilities in the sandbox processing itself, the IPC processing. But there are many uncommon approaches that can be valuable to an attacker, things like logic errors in the dialogues, mishandling of privileged handles, clipboard bugs, abuse of symbolic links. Those are all very possible ways and vectors out of the sandbox. With your understanding of the sandbox itself, you can possibly find new ways to actually break out of the sandbox. The Zero-Day Initiative is a bug bounty program. We do purchase privilege escalations and sandbox bypasses. So if you discover a sandbox bypass, we obviously purchase those and we'll disclose them to the vendor. If you use some of this information in our slides, we'd love to hear it and to find your sandbox bypasses and get them fixed. Thank you.